So acid derivatives. Well, we saw the acid halide, and their nomenclature will be oil halide. So butanoyl chloride, benzoyl bromide. These lack hydrogen bonds. They don't have the hydroxyl group anymore. And so they have generally lower boiling points than their corresponding carboxylic acids. But they have very similar reactive properties because the chloride and the bromide can also act as leaving groups, just like the hydroxyl group can. Acid anhydrides are, as their name suggests, two carboxylic acids that have been dehydrated. A condensation reaction has occurred, pulled out water, and they are now anhydrides. Acetic anhydride, butanoic, propanoic anhydride, so that's our nomenclature. And you can see how it's basically like putting two carboxylic acid groups together and just pulling off an H2O. H from one side, OH from the other side. And then we have amides. Also a condensation reaction. You have an amide forming when an amine reacts with a carboxylic acid, or for that matter, an ester. Okay? So an amide is where I have a carbonyl directly bonded to an amine, so amide. And you can see the nomenclature here. Whenever I have R groups coming off of the nitrogen, it'll come with a prefix N. So for example, N-methyl benzamide tells me that the methyl is attached to the N, the nitrogen. These are generally very weak bases. The electronegativity of the nitrogen, or sorry, of the carbonyl dramatically decreases its ability to act as a base because it destabilizes it. We saw that in the demonstration a little bit earlier in the animation that I showed you. And they're roughly equal to esters in solubility. So describe esters in a moment. Acid halides, again, they can be formed from thionyl chloride, phosphorus trichloride. Those are both chlorinating agents. You don't need to know the difference between them. Or something like phosphorus tribromide. Amides, again, they can be formed from carboxylic acids or potentially esters or potentially acid halides. They all have very similar reactivity because they all have leaving groups, plus an amine forming an amide. Acid anhydrides, these are formed from the condensation of carboxylic acids. So I can have a carboxylic acid plus a carboxylic acid, or I could even have a carboxylic acid plus an acid halide. Again, they have very similar reactivities, and so you can sort of mix and match them and interchange them. Okay? I can also get cyclic anhydrides. Two carboxylic acids in the same molecule makes this cyclic molecule. Now let's talk about some of those nucleophilic substitutions. Nucleophilic substitutions can happen with carboxylic acids and with all of these other acid derivatives because they are acid derivatives. They all have leaving groups that can come off relatively easily depending on the compound. So acid halide can revert back to a carboxylic acid where water acts as a leaving group. I can go forward with this reaction and revert it relatively easily. Acid halide plus an alcohol is just like the carboxylic acid plus an alcohol. Again, nucleophile comes in, attacks the electrophile, and leaving group, the chloride, comes off. Acid halide plus an amine makes an amide, just like carboxylic acid plus an amine as an amide. So we're starting to see a lot of common themes recurring over and over and over again. And this is why I tell students all the time, you have to know these basic foundational principles of reactions. Nucleophile attacks electrophile, leaving group comes off, or leaving group is bad. Understand why certain compounds are more or less stable with the electronic induction in that animation that we saw. And when you understand those basic foundational principles like the back of your hand, you're in a much better position to basically interpret any of these specific individual reactions because you understand how molecules interact. Acid anhydrides. Okay? These will also undergo very similar reactions as before. We can hydrolyze them, add water, bring them back to a carboxylic acid. I can treat it with an alcohol, make an ester and a carboxylic acid. Again, these mechanisms are very straightforward and generic and consistent with the principles we've discussed already. Okay. So let's try some practice problems and apply what we discussed. Go ahead and give this problem a shot. Okay, so I've got this ammonia right here, which is going in, and you can see it's forming an amide and a carboxylic acid after reacting with this acid anhydride. Okay. Same foundational principles as before. I know I've never actually shown you how an amine, ammonia, is going to interact with an acid halide, but I don't need to have shown it to you in order for you to be able to answer the question. It still relies on nucleophile, attacks electrophile. In this case, leaving group comes off. So who's the nucleophile here? The nucleophile is the electron-rich species, the ammonia. It has the lone pair, it's electron-rich, and consistent with basically all of the other reactions, the carbonyl carbon is the electrophile. So that comes in, it breaks this bond, and end up adding the amine here to make the amide. So the first step is the attack of the nitrogen lone pair on the carbonyl carbon. My answer here then is D. Okay. So that was consistent. Let's try this one. Okay. Again, nucleophile attacks electrophile, leaving group comes off. Lots of common themes here, but you can see that they're not all going to be asked in the exact same way. They're not going to always explicitly ask you, what's the first step? Or who is the nucleophile? Or what's the electrophile? Or what's the product? Right? Sometimes it might be a little bit trickier like this. We have this 18O labeled oxygen. So what we're basically trying to do is understand, given the generic mechanism, which atom is going to end up, or where is that 18O labeled oxygen going to end up? This is isotopic labeling. It allows us to track where an atom ends up in a mechanism. And so we're going to deal with this like we've dealt with any of the other reactions. Who's the nucleophile? It's the methanol. It comes in, it attacks the electrophilic carbonyl, surprise, surprise, and the leaving group comes off. So if we think about much more closely now about what happens here, when the methanol attacks, I'm going to get the 18O labeled oxygen with the methyl group. And then this OH comes off. So the 18O labeled methanol, or the 18O labeled oxygen, is right here. It's this new oxygen. Okay? The carbon-oxygen bond right here remains. It doesn't get broken. So we're going to leave that one alone. And that means that it has to stay here. Okay? It's still fundamentally the exact same question as the one on the previous slide. It's just being asked from a slightly different angle. And it's important to have that flexibility in terms of understanding what you're really being asked to do. In most cases, it's, for questions like this, interpreting how the mechanism occurs. Okay? So, hydrolysis of fats and amides. We've looked at the saponification reaction before, but when I showed it to you, what I gave you was the carboxylic acid, the free fatty acid. But fats and lipids, not all lipids, but fats are often basically triglycerides. And triglycerides are these, or sometimes called triacylglyceride, these ester bonds. So in the presence of a base, we can actually break this apart. I'll get glycerol out, that's a glycerol molecule, and 3 fatty acid salts, 3 soap molecules. And so that's another way to get saponification to occur. And hydrolysis of amides, we've seen this reaction already. Very much the similar reaction. water comes in and hydrolyzes the amide bond. Generally, this requires an acid catalysis, but of course proteases, enzymes which will break apart proteins, can catalyze this reaction as well. Okay. Keto acids and esters is a specific type of ketone / carboxylic acid. It's my keto acid. See, alpha, beta, gamma keto acid, depending on where the ketone is with respect to the carboxylic acid. Okay. These can be synthesized usually from the deamination of amino acids. So we'll take amino acids, we'll pull off the amine, and what's usually left is some carbonyl or carboxyl group. Usually used for fatty acid synthesis, and the beta keto acid can undergo a decarboxylation reaction. So the angles there are nice, and what you should just know is that a decarboxylation reaction involves the loss of a carboxylic acid. So you lose a CO2 in the formation of that molecule, right? Esters, as you can see, their nomenclature: methyl propanoate, ethyl butanoate. The methyl or ethyl nomenclature, the one that comes first, is the one that is esterified onto the compound. The propanoate, butanoate refers to the molecule that's actually attached to the carbonyl. That molecule does not come off because it's not a good leaving group. Okay. They're more polar than ethers, but they are less polar than alcohols. Okay. They can accept hydrogen bonds because they have the carbonyl, but they can't form hydrogen bonds within themselves like carboxylic acids can. So they're generally more volatile than corresponding similar carboxylic acids.
For most students, and maybe you too, the CARS is the hardest section on the MCAT. It may feel like it's one of the few remaining obstacles between you and the medical school of your dreams. But as you try to prepare for the CARS, you find there is a never-ending stream of conflicting tips, strategies, and plans, none of which seem to actually help or show any results. If you feel frustrated, overwhelmed, or lost when it comes to the CARS, if you're looking for a CARS expert who has helped thousands of students achieve their MCAT CARS goals, then you found your solution. Testing Solutions MCAT CARS Bootcamp. Founded by Nick Zahner, a current medical student at Stanford with a master's degree in philosophy of religion from Harvard, Testing Solutions' approach to the CARS is revolutionary. Testing Solutions CARS Bootcamp provides day-by-day, step-by-step instruction that teaches you the techniques that produce ultra-high MCAT CARS scores. Instead of wasting your time with the needlessly complex filler that other companies try to sell you, Testing Solutions' approach to the CARS is based on the principle of minimum effective dosage. There's no wasted time, just the minimum amount of effort that is required to get you the results you want. With over 500 4.5-star reviews on Amazon, Testing Solutions CARS Bootcamp is the most trusted, proven, and effective CARS course available on the market today. You will have access to Testing Solutions' 180 meticulously designed CARS passages, the largest CARS practice library offered by any MCAT prep company in the country. Our passages are regularly rated by users on Amazon, Reddit, and SDN as the most accurate non-AAMC CARS practice passages available, consistently rated higher than Exam Crackers, the Princeton Review, Kaplan, and Next Step. Unlike some companies who prey on pre-medical student fears by charging outrageous amounts of money for their mediocre at best practice materials and courses, Testing Solutions will always charge a fair price for an amazing product. Because after all, we're not like the other test prep companies. We're aspiring doctors just like you, only a little further down the path. Let us help you do what we've already done. If you're not happy with your CARS Bootcamp for any reason, we offer a 100% money-back guarantee, no questions asked. You've got nothing to lose and the CARS score of your dreams to gain. Don't be one of the people who write us each week saying they wish they had found our MCAT CARS Bootcamp sooner. You don't have to struggle with the CARS any longer. Sign up and get started today.